Hi everyone. In this lesson, I'm going to briefly talk about the significance of multi-scale stress and strain in the study of natural deformation. In mechanics textbooks, a physical quantity at a point is defined in terms of a limit. For example, the density of a material is defined as the ratio of mass over volume in the limit of the volume element approaching zero. The limit is taken to ensure that the density is truly at a point, as opposed to the averaged density in a finite volume. Similarly, the traction, the total stress, acting on a plane is defined as the force divided by the area in the limit of the area element approaching zero. Again, the limit is taken to ensure that the stress is a point quantity. Once the quantity at a point is defined, then we can speak of the spatial variation of the quantity to define a field. Like the stress variation defines a stress field, the variation of displacement defines a displacement field. The limit definition of a point quantity in continuum mechanics is based on the assumption that the material is continuous mathematically. But real materials have inherent characteristic scales. Think about how we would get the density of granite. To get the density, we would need to have a sample that contains enough mineral grains to adequately represent the granite. If the sample is too small, the density may not represent the granite. When the sample size becomes too small, what we get might be the density of a quartz grain, for instance. There is a critical representative volume, Vc, below which the density fluctuates a lot and is not the density of the granite. Therefore, the density of granite must be an average density over a finite volume. In fact, the density can be regarded as a volume-weighted average of the densities of mineral grains contained in the critical representative volume. V alpha here means the volume of the alpha's grain. Rho alpha is the density of that grain, and the Vc is the critical representative volume. So for real materials, a local point quantity is always an average over an representative volume element that is appropriate for the problem. Many problems in geology require consideration of multi-scale representative volume elements, and therefore we need to talk about multi-scale stress and strain. As structural geologists, we are interested in structures and fabrics directly observed from outcrops and smaller scales. Because rocks are heterogeneous, our observations are inevitably from rheologically distinct elements, RDEs. To understand these structures, we must consider the deformation inside individual RDEs, which requires a small-scale representative volume element. On the other hand, we wish to relate our studies to the tectonic scale deformation in which our observations are made, and this needs consideration of the deformation at a much larger scale, with a suitable representative volume element that contains many rheologically distinct elements. Here is a real-world example that requires a multi-scale approach. Keeling et al. Published a paper in Journal of Structural Geology of a malonite. The malonite consists of quartz porphyroclasts in a matrix of dynamically crystallized quartz and mica, etc. The foliation pattern and their shape fabrics defined by the quartz porphyroclasts both indicate a clear strain gradient, like this green arrow. Strain increases in this direction and there is an unambiguous top to the right sense of shear. The quartz porphyroclasts themselves are deformed and dynamically crystallized. They presented beautiful data of quartz CPOs from different quartz porphyroclasts. They noticed that the quartz CPOs are variable from class to class and seem to give conflict sense of shear that are hard to interpret. As each quartz porphyroclast is a rheologically distinct element due to their shape, orientation, and anisotropy, it is not adequate to use the shear zone scale flow to interpret the CPOs. The CPOs in each porphyroclast is related to the partition deformation in that porphyroclast. When these two scales of deformation are considered separately in a study by Bandari and Jain, we were able to reproduce the quartz CPOs that is observed by Keelan et al. Another example is isolated L-tectonites reported in many places. L-tectonites are deformed rocks with a strong lineation but weak or no foliation. Most L-tectonites are reported to be in isolated volumes, often in mechanically more competent volumes. An excellent example is from North Chaidam in China. There, L-tectonites are observed in granitoidal rocks, embedded in a schistose rock mass. Yang et al. Conducted a multi-scale modeling for the development of such L-tectonites. They show that L-tectonites can be developed in any high-strand zone environment as a result of deformation partitioning. In the past, L-tectonites has often been interpreted as due to homogeneous transtension deformation in the Sanderson and Marchini sense, although such a mode of deformation has never been reported in nature. So many problems in geology can be tackled by considering two separate scales: a microscale deformation in an rheologically distinct element, and a macroscale deformation that deforms the RDEs themselves. To address such problems, we must consider two important concepts. They are partitioning and homogenization. We will get into more details on these concepts later. A simple introduction is given in this lesson in the context of multi-scale stress and strain. Let us consider a macroscale representative volume element, as schematically shown in this case of a conglomerate. So the macroscale representative volume element is made of many rheologically distinct elements. The stress and strain in each of these rheologically distinct elements, RDE, are denoted by lowercase sigma and epsilon. So sigma alpha means the stress in the alphas, RDE, and epsilon alpha, strain in that RDE. F alpha means the volume percentage of that RDE in the representative volume element. The overall scale stress, the macroscale stress, that is the stress on the scale of this macroscale representative volume element, is represented by an uppercase sigma. As we discussed earlier on, this macroscale stress is the volume-weighted average of microscale stresses. The same is true for the macroscale strain. The stress-strain relationship for each RDE is represented by a rheological equation like Hooke's law. Now, how do we relate the macroscale stress to the macroscale strain? By an effective stiffness. So this C with a bar on the top stands for the overall stiffness. The procedure to do this is called homogenization. On the other hand, the stress and strain in an RDE can also be expressed in terms of the macro scale stress and strain by a relationship like this. And these are called the partitioning equations. So partitioning relates local field to the bulk field, and homogenization is the procedure to get the overall behavior from behaviors of constituent elements. The formulation of partitioning and homogenization expressions are objectives of micromechanics that we will discuss later on. But we can discuss some simplistic homogenizations now. Our objective is to determine the effective stiffness, C bar, from constituent properties. We can carry out the averaging using the stress-strain relationships of individual RDEs to get to this, but no further. We're not able to get C bar with this operation. We can move forward if we make simplistic assumptions. If we assume that all strands are uniform, so the strands in all phases are the same, then this strand is a constant and can be moved out of the angle brackets. We get C bar as the volume weighted average of the stiffness of RDEs. This is called the void average. If we make the assumption that all stresses are uniform, then we can use this relationship and move the stress out of these angle brackets because the stress is a constant. With this, we get this relationship. So the homogenized compliance is the volume averaged compliance of RDEs. Take the inverse of these compliances, we get the overall stiffness, and this is called the Roy's average. People also speak of Voigt, Roy's, and Hill average, which is just the average of the Voigt average and the Roy's average. Geophysicists use this a lot. Uniform strain is the upper bound. A special case the uniform strain may apply is a situation where all the constituent phases are layered and the deformation is stretching or compression in the direction parallel to the layer. In this case, all the strains are required to be the same. The stress-strain relationship in each layer is sigma I equals the Young's modulus of that layer multiplied by the strain of that layer. Because the strain is the same, right? It's a constant. So the overall stress is the volume weighted average of the stress in every layer. It's this operation, and this leads to this relationship. So the homogenized Young's modulus is the volume weighted average of the Young's modulus of individual elements. The uniform stress model is called the Sachs model. It is like a simple shear setting of a layered material. In this case, the shear stress must be the same in every layer. The overall strain, capital gamma, is the volume weighted shear strain of the constituent layers, and it's this. This leads to Roy's average. Here are some quantitative calculations of the various averages for a two-phase material. Starting with a uniform material with a shear modulus, say mu0. Now, let's add a second phase, all spherical. The second phase can be stronger than the initial phase or can be weaker than the initial phase. On the left is a situation when the second phase is strong. It's 50 times stronger than the first phase. And on the right is the situation the second phase is weaker. It's only 2% of the first phase. Vertical axes are the effective stiffness, so it's the stiffness of the overall material, normalized against the initial material. So if the second phase is strong as we increase the concentration of the second phase, the material gets stronger. If we use the void average, the effective stiffness goes this way, increases rapidly as we increase the concentration of the second phase. Roy's average gives this relationship. So the effective material is much weaker than the prediction of the void average. So the Roy's average gives the low bound and the void average gives the upper bound. Unfortunately, the two bounds are far apart. When the second phase is a weak phase, it's a similar result except that the material gets weaker as we increase the percentage of the second phase. Again, the void average gives a higher estimate of the effective material and the Roy's average gives a low bound estimate. More sophisticated averaging using micromechanics gives prediction of the effective stiffness between the void and the Roy's. Uniform strain and stress are certainly unrealistic, but they are useful as bounds. In viscous deformation of mixed strong and weak phases, like the deformation of a granite, it's made of feldspar and quartz and mica. In the Euler deformation, the deformation is more like uniform strain. As deformation continues and the mononatization takes place, the weak phase becomes more strained and become connected. The deformation becomes more like uniform stress. As mononatization continues, the rock weakens substantially, and the ultimate strength gets closer to the weak phase, Roy's behavior. Okay, here is a quick summary of the main points covered in this lesson. Local stress and strain is defined always in terms of a representative volume element suitable for the problem. Multiple representative volume elements need to be considered in rock deformation, and that leads to multiple scale stress and strain. Many problems require considering two separate scales, a microscale deformation in RDEs, rheologically distinct elements, and a macroscale deformation in which RDEs themselves deform. The expression of microfields in terms of the macrofield is called partitioning, and the procedure of getting the properties of the macroscale effective material from properties of RDEs is called homogenization. Partitioning and homogenization are dealt with in micromechanics. Void Roy's and void Roy's-Hill averages are simplistic homogenizations that provide bounds for the effective material. That's it for this lesson. Thank you for your attention.